Welcome everybody, thanks for gathering with me. I'm going to talk about another article now, Binary Secrets in Missing Masses, what the Hubble Space Telescope found in the classic open cluster NGC 2158. Here you can see 2158. It's a small, dense open cluster right next to Messier 35 in the constellation of Gemini. I actually just observed and sketched it about 3 weeks ago. I haven't processed the sketch yet, so that's the image from the sea star here. But deep within that cluster, recent observations from the Hubble Space Telescope have provided an incredibly detailed look at stellar population, uncovering new insights into binary stars, mass functions, and unique M-dwarf discontinuity. So when we look at NGC 2158, like I said, it's an open cluster. It's long intrigued astronomers and amateurs due to the dense population and its position in the Milky Way. It's located near Messier 35, like I mentioned, which is a much larger open cluster. This cluster always has intrigued me. It's beautiful in my vision. If you can get M35 and 2158 in the same field, just gorgeous. This recent deep Hubble Space Telescope view allowed researchers to push further into the cluster's lower mass stars than ever before. By analyzing the observations, the team was able to map out several key characteristics of the cluster. They looked at binary star fractions. One of the paper's most striking findings is that NGC 2158's binary fraction is not a fixed number. While previous cluster studies have assumed a constant rate, this deep Hubble view shows a sharp decline as mass decreases. High mass stars greater than 1 solar mass are 50% of those are binaries. Low mass stars from about less 0.2 solar masses. So, and again, a solar mass is the mass of our sun. They're only 11% are binaries. So you can see that if they're 1 solar mass, the mass of our sun or greater, 52% of those are going to be binaries. If they're only about 0.2 the mass of our sun, then only about 11% are going to be in binaries. This mirror image of the galactic field suggests that binary formation in intermediate age clusters like NG 2158 follows the same rules as the rest of the Milky Way, rather than being dominated by the cluster-specific internal environment. This matched what we have found in other open clusters of the same age. The mass function, M-dwarf. So the other thing that the paper does is looked at mass function. The paper identifies 3 distinct slopes of how the cluster's mass is distributed. High mass, 2.49, a steep decline consistent with the standard Salpier IMF. Low mass, 1.11, a shallow slope as you move towards stars similar to our sun. And then very low mass, 0.08, a nearly flat distribution below 0.3 solar masses. The study found a pronounced deficit of stars below 0.3 solar masses compared to the current models. This suggests we might still be overestimating how many tiny stars are actually born in these environments, or that the cluster is losing its smallest members to evaporation faster than is expected. M-dwarf discontinuity, the researchers detected a sudden break in the main sequence at approximately 0.3 solar masses. This is a phenomenon rarely seen so clearly in a cluster. The physics behind it is that this is linked to the 3 He-driven instability for convective kissing instability. In stars around this mass, the transitions form a radiative core to being fully convective triggers a sudden change in the nuclear luminosity and thermal readjustments. Why it matters, this gap is well known in field stars like the JL gap, but finding it in NGC 2158 allows astronomers to test stellar evolution models against a population where every star is the same age and metallicity. Why it matters for us? Well, we may not see the M-dwarf discontinuity through our own eyepieces at our own scopes. Knowing the underlying skeletal structure of a cluster like NGC 2158, that adds a layer of depth to the experience when we observe it. When you're at the scope, you're not just looking at a smudge of light or a collection of pinpoints. You're looking at a dynamic system where the ratios of single stars to binaries and the distribution of stellar masses are currently being rewritten by data from the Hubble Space Telescope. Whether you're pushing your telescopes to its limits or imaging the dense core of an open cluster, it's research like this that reminds us how much there is still to learn about even the most familiar objects in our night sky. There's the link to the paper. I invite you to go take a look. Thanks for joining me.